Hello, my name is Gavin Butts, and this is Math 323, Real Analysis. And today we're going to be proving the intermediate value theorem for derivatives. What does that mean? I could hear you asking. That's a great question. So, the intermediate value theorem for derivatives states that let f be a real valued function defined on a closed interval from a to b, we're going to say here. That maps to the real number line, and it's differentiable. And for all m in real numbers such that m is between f of a and f of b, then there exists a t in between a and b, but not a or b, such that f prime of t, the derivative of f at t, is m. We're going to prove that today. So let's get right into it. Okay, so let's start it. So we're going to say that g of x is a new function. We're defining it ourselves, so we can really do whatever we want. We're going to say that g of x is equal to f of x minus mx. Why? Well, we'll get to that later. It's kind of hard to explain why right now. So let's just find out what we know about g. So since f is differentiable, f is also continuous. All right. And also, we have this other term, mx. mx is also differentiable and continuous. So, because each of its linear terms, f of x and mx, are differentiable and continuous, g is also differentiable and continuous. We do know a little bit more than that. We know what the derivative of g of x is. So let's state it. We have g of x is equal to the derivative of f of x minus, subtraction is a linear operator, and derivatives expand over linear operators. So we have f prime of x, derivative of f, and m. Okay, so keep this in mind. We'll use this tool later. So let's start with considering our function. This is all from our hypothesis here. Derivative of f at a is less than m, and m is less than the derivative of f at b. So let's do some algebra with this statement here. So first, let's just subtract m from each term. So we're going to do some gymnastics here since I'm using two colors. All right. Okay, so what we've done here is just subtract m from each term. And now we can do some simplification. We know that m minus m is 0. Okay, and then this is also the statement. This is our definition of g. But the only difference is that we're defining x to be a. So we have, let me get there. Okay. Oops, not f. I just said is g. Okay. So we have g prime of a. And similarly, this is the exact same thing defined at b. So we have g prime of b. All right. So we've got our key facts from what we just showed right here. We're going to come back to these as we need them. So since g is continuous, showed that earlier, it is bounded. And by theorem 18.1, this implies that there exists a t in between a and b such that g of t is less than g of x for all x, in our interval. I'm losing color. Hopefully you can still see that. In between a and b. And by definition, this means that g of t is a minimum. All right, so we'll come back to this. Consider the derivative of g at a. So the formal definition, the derivative of g of a is equal to the limit as y approaches a of g of y minus g of a over y minus a. And we know some facts about this from earlier. Right here, we showed that it's less than 0. So let's bring that in. It's less than 0. So this is negative. Since it's negative, at least one of these values, gy minus ga over y minus a, must be negative. And not both, because if it were both, it would be positive. All right. So since y is in a and b, a to b, on the open interval, it's not a, because we're taking the limit as it approaches a. that means that y has to be bigger than a. So y minus a is greater than 0. So if this is positive, that means that this value up here must be negative, so less than 0. So since g of y minus g of a is less than 0, this means that g of y is less than g of a. And what does this tell us? There's a value in a and b, so we can call that y naught in our value of a and b that's less than a. So we know that a is not our minimum. So next, we're also going to show that b is not our minimum, but we'll get to that in just 1 second. Okay, we're on our home stretch. So we've added 2 more facts here that we'll refer to later and that we just proved. So now we're going to do the exact opposite. As I stated, we're going to consider g prime of b. So g prime of b is equal to the limit of, as y approaches b, of g of y minus g of b over y minus b. As we stated, g of b is greater than 0 this time. We ran out of space, so we'll put it there. So since it's greater than 0, either its numerator and denominator are both positive or they're both negative. We don't know exactly which yet, so let's take a look. So since y is in a and b, y is not b since y is approaching b, as was the case when we were dealing with a. Y is less than b, so y minus b has to be negative then. Okay, so since our bottom is negative and our holding is positive, that means our top has to be negative too. So there exists a y naught in a and b. It's kind of like a little version that we're referring to as y here, so that g of y naught is less than g of b. Okay, now because g of y naught is less than b, g of b can't be our minimum. So t is not b. Similarly, we know t was not a. And because we knew t, our minimum, was between the closed interval a to b, and we know it's not a or b, we can further clarify that it's within our closed interval a to b. Okay, we're almost there. So, by Fermat's theorem, because our value is defined on the open interval and our function g is continuous and defined on our interval, we know that it attains that g prime of g, the derivative of g is 0 at its minimum. And that's what we're saying right here. So now, making it their correct markers, let's do some final substitution. We know g prime of t is equal to f prime of t minus m. So f prime of t, minus, I got a lot of colors here now, m equals 0. Equals 0. Okay, and because of algebra, who doesn't love algebra? F prime of t is equal to, okay, this is my left hand, so you have to forgive me. G prime of t is equal to m. What does our hypothesis say here? T is on the open interval, and f prime of t equals m. It's exactly what we just said here. T is on the open interval, and f prime of t is m. That's it. That's the proof. I hope you enjoyed it. I would say watch next time, but there probably won't be a next time. Bye-bye.